In this video, we're going to start an exploration of vector multiplication. We've already done this a little implicitly, but we're going to formalize how we handle that here. The challenge with multiplication of vectors is there are actually several different ways to do it, several different ways that satisfy our usual intuition about what multiplication means. We're going to focus on two particular multiplication styles in Math 121, scalar multiplication and a dot product. Scalar multiplication we've already seen before, and this would be something along the lines of 3 times some vector. And that multiplication, the key thing there is that the element out front is a scalar. So we call it scalar multiplication because the building block is a vector, but what we're multiplying it by is a simple non-directional scalar value. When we do this kind of multiplication, we get what we'd expect, which is if we take this vector and multiply it by 3, we're going to have a vector that's 3 times as long. So imagine if we use this as adding the same vector to itself, we would have 2 times that vector, or we could represent that as 2 multiplied by our vector. Notice we also have an absolute value sign in here, and that corresponds to the option of putting a negative value out front. If we have a vector and we multiply it by a positive value, then we simply scale that vector in the same direction. However, if we have a negative multiplier and we multiply a vector by some coefficient that is not positive or is negative, it will reverse the direction and also change the length at the same time. The length change is dictated by the magnitude of that number. So if it was 3, the element would be 3 times as long. If it was negative 3 that we multiplied by, it would still be 3 times longer, but it would be flipped into the opposite orientation or opposite direction. All of this scalar multiplication blends seamlessly with what we've done before with addition of vectors or subtraction of vectors. So most people find this part fairly intuitive. Let's explore that in a concrete form with a vector that we're going to make up, looking at that vector here and calling it v. If that's our vector v, then 2 times v, again, we can think in the analogy of 1 times the vector, then the second time of the vector. The entire length that we get as a result is going to be 2v. Same direction, twice the length. All right. What about 0 times v? Well, if we take that 0 value and multiply it, we would end up with length of 0. Just like we ended up with twice the length when we multiplied by 2. And that turns our product, 0 times v, into the interesting 0 vector, which has 0 length and no specified direction. It's the only vector that has no direction associated with it because we're not going anywhere. So 0 times any vector will always give us this 0 vector, or a dot if we're representing it graphically. If we take negative 1.5 times v, again, we're going to draw v again, have a root. If we take that same vector and multiply it by 1.5, it'll get 50% longer. But then the negative sign tells us to change the orientation and change the direction. And there's about 1.5 times the length. That would be negative 1.5 times v there. 50% longer. Or if you like, 1.5 times the length. But unlike the earlier calculation where we ended up in the same direction, we end up in the opposite direction. And that's how we would do these calculations of scalar multiplication with a vector graphically. When we consider vectors presented to us in component form, the operations are very similar. If we had 2 times v, when we write that out in a non-graphical way, but simply as a calculation, the way we handle this multiplier is to extend the length of each component by 2. And so we can think of that as distributing the scalar multiple onto x and onto y, just like a polynomial or some other expansion process. We get 5 times 2 is 10, 2 times negative 2 is negative 4, and that would double the length in x, double the length in y, and result in a vector that's twice as long as the original. If we do the same operation with the 0 multiplier, all the same elements apply. We distribute the 0 inside, but 0 times anything is simply 0. So we get our 0 vector, no x and no y distances included. Last but not least, if we have 1.5v but with a negative sign, the calculation process is identical. What we're going to see is this negative is going to invert the direction in x. The original vector was 5 to the right, and now when we do this multiplication, we're going to end up with a negative x component, so it'll be going left, changing the direction, and likewise, we were going down in y originally. When we multiply it by negative 1.5, we'll be going up, and we'll end up with a positive y component. So this calculation process, distributing the scalar onto the x and y components, is identical regardless of what the actual coefficients are or the vector is. One of the other things we're going to need to do with vectors is add, subtract them, and combine that with the scalar multiplication. The list of rules is here, but essentially they're everything that you would expect in terms of normal addition, subtraction, multiplication. So there's no real surprises here. Let's take one example here. If we had distributivity, if we had 2 plus 3 times some vector, we could write that as 5 times the vector, or we could write it as 2 times the vector plus 3 times the vector. And that jibes, that aligns with what we usually do with any scalar quantity here. The fact that it's a vector doesn't actually change how we manipulate things. So review this at your leisure, but essentially your intuition is going to be a pretty good guide for how to handle scalar multiplication and addition.